Thank you. Well, good morning, everybody. I'm very sorry I can't be with you in person, but thank goodness we have technology and I can be with you virtually. So yeah, my talk is entitled Magical Multiharmonic Multiphase Machines. But before we get there, I want to back up and just give a little bit of an overview of what we've been up to, what my group is about, and what we've been up to since last annual review. So I'm going on about 5 years here as part of the Madison community, and I'm a faculty member in WEMPEC. My group focuses on electric machines, or very electric machine centric. These are pictures of kind of what our research looks like. And we tend to be at our best when we're doing research at the intersection of some kind of weird electric machine, either a high torque or high speed motor, controls, and frequently magnetic levitation. And so we've got projects going on that feature purely magnetic levitation, like magnetic bearings, projects that are motors with magnetic levitation, such as a bearingless motor, and projects that have no magnetic levitation, but are doing unconventional things with machines, like merging hydraulics and electric machines into a single device. And so you're going to hear a little bit about all of this in our presentations and at the poster session. And so, yeah. Well, since last annual review, I put together a bit of a photo collage of what's been going on with us. And one of the things is that we finally got a group picture. So my research group was just kind of hitting its pace, getting momentum, being of a reasonable size to take a picture right before the pandemic happened. And so we never got around to taking a group picture because it was winter and you know, it wasn't on the top of our list. And then what do we know? We all went virtual. So anyway, I'm really proud to get to show you a picture of all the great students that are doing research with me. And we got a great day. The trees outside Engineering Hall were just starting to blossom. So around the lab, I've got 2 slides here of all my students. I asked everybody to send in a picture of them doing something cool in the lab. Now, we've been really busy in the lab this last year. By my count, we have either built or for the first time tested 7 different electric machines within the last year, which is a lot. You can just ask Kyle and Pia. We've been pounding on their doors, asking for help frequently. And so that's reflecting these pictures. You can see a lot of people assembling and testing their machines for the first time. And so, yeah, our research, everything from Anvar working on some power electronics here. Steve is building an AC homopolar motor that you can see during the poster session. Imtiaz with a high-speed bearingless generator. Nathan, you'll have to come and check out his poster. He's got a live demo of a bearingless motor levitating and operating down in B330. And Parth is a new face in my lab. He'll be working on linear machines for a hydraulic system in an off-highway vehicle. Federico here is actually a merger of the Ludus group and the Severson group. He's co-advised with myself and Dan Ludus on electrostatic levitation. And Bharat, you'll have to check this out in the poster session. This is how electrical engineers abuse a CNC mill. He is retrofitting the CNC mill to operate as a bearingless motor dynamometer. And so that's going to be down in B533. Martin's building up some electric machine windings. Nishant is fabricating an axial flex machine, and you'll hear him talk just after me. And Jojo here is demonstrating 2 bearingless motors on a single shaft. You'll have to see this during the poster session. She's got this levitating down in B330. This is kind of a unique setup because she's able to operate these 2 bearingless machines with 25% fewer power electronics. And it's quite a fun demonstration, an interesting feat. All right, so apart from research, you heard Professor Hagnes mentioned that my group's been active in some outreach activities. Last year at annual review, I had a couple of slides called Learn to Use the Force. This year, I've got a couple of slides called Use the Force. So we've learned to use it, now we're using it. This is an initiative to engage youth, elementary school and middle school youth, in experiments with basic electricity and magnetism to try to help them build STEM identities in electric machines, electromechanical energy conversion. And so we put together really simple kits: magnets, bolts, paper clips, batteries, alligator clips, these kind of things. And last year we shipped it out to students across the state of Wisconsin, met them on Zoom and did some stuff on Zoom. This year we turned it into what we called an interactive experimentation station. And we took this booth basically to a couple events on campus. We're going to do more this summer and fall, and then invited youth to come up and try some really, it was kind of student led. They got to experiment, what happens when you hook the paper clip, or hook the alligator's clips up this way or that way. And it was a lot of fun. I've got some pictures here of what this looks like in action. You'll notice all these folks in red shirts are not only my students. We were really fortunate to be part of the WEMPEC community. And I sent a call out asking for volunteers to help us staff the booth. And we had more volunteers than we had spots to volunteer for. And so it was really great to have this kind of be a WEMPEC wide effort to engage with youth. And the youth loved it. We had kids that would camp out at our booth for like an hour, trying all kinds of different ways to connect things up. So it was just really fun to see and do and get people excited and hopefully inspire the next generation of WEMPECers, maybe 2 generations out. All right, so let's get down to it. Magical multi-harmonic multi-phase machines. So this jargon-filled title is meant to be kind of a lighthearted talk, believe it or not. So I'm trying to put together some material here on that looks at multi-phase machines in a little bit of a different way than we normally think of these machines. And so the talk, it's not necessarily about any one whiz-bang great research innovation, though there is some whiz-bang research innovation in here, and I'll point that out. But it's more just meant to provoke some curiosity, to be playful, to be fun, to get you to think in maybe a little bit of a different way, and also with a motivation of getting you to come and see our posters and set up some of the cool stuff that my students are going to talk about after my talk. So with that, let's get started here. What is a magical multi-harmonic multi-phase machine, other than something that's hard to say 10 times fast? So I'm going to start backwards here. What do I mean when I say machine? I'm talking about a rotating electric machine. So, a motor or a generator. These are all pictures of machines we built this last year. You can come and see them in B330 or B533 during the poster session. Again, I'm going to keep shamelessly plugging the poster session. And what is multi-phase? Well, a multi-phase machine in the context of this talk is any machine that has 5 or more connections to the drive electronics. So a 3-phase machine is not a multi-phase machine because it has 3 connections to drive electronics. It's not a single-phase machine either. It's a machine with 5 or more connections to the drive electronics. So we hear about multi-phase machines. In some circles, we hear about them a lot. Usually when we hear about multi-phase machines, we're talking about using them for some kind of fault tolerance or redundancy. If one phase goes down, you've got more phases left, or to reduce as a means of reducing the phase power rating for the power electronics. However, this talk is about neither of these. This is about something else. So what is it about? This talk is about creating multiple air gap fields from the stator winding. So when I say multiple air gap fields, I actually mean, at the end of the day, you have a single cumulative field in your air gap, but I mean a field that has multiple harmonics in it. And so this orange trace here, this is a good plot to drill down on for a second, because I'm going to show plots like this frequently. So on the y-axis, I'm showing that the magnitude of the air gap field as I traverse around my air gap in the counterclockwise direction. And so this orange trace is showing, like a square wave. Well, we all know square waves are composed of, an infinite series of harmonics. And so I'm drawing each of those harmonics down below here. And so when I say a multi-harmonic machine, I'm talking about a machine that has an air gap field that contains multiple harmonics. Okay, great. But what's magic? Well, the magic is that we're going to be talking about machines that can independently control all of their harmonics, or the major harmonics. And so that's where we get into the Hogwarts school of WEMPEC here. We're gonna be talking about, that's where the magic is. We're gonna talk about machines that we can make these fields do weird things. They can rotate backwards, they can rotate forwards, they can grow, they can shrink. Yeah, so that's where the magic is. And so the magic equation, this is what we're gonna be talking about over and over here, is that we're taking an electric machine, we're adding a drive, and we're getting out our crazy field behavior. And so we'll be talking about both sides of this. We'll be talking about first the machine aspects, what it means to create multiple harmonics in air gap, how you do it, what kind of currents are required. And then after that, the second part of this talk will be about how you connect your drive up to it to make those currents happen. So why would you want to do this? Well, there's three circles of research, three camps of research where people talk about this a lot. They don't word it quite like, they don't call it magic. They don't word it quite like I'm talking about it here, but it's essentially the same thing. The first camp is for enhancing torque. The second is for creating normal forces, bearingless machines, something we like a lot. The third is for wireless power transfer, conveying power to the rotor of a synchronous machine, of a wound field machine for the field excitation. So I've got a slide on each of these here. Torque enhancement. Well, what the heck? Why do you need multiple harmonics to enhance your torque? So just as an example from a permanent magnet machine, the same principles apply to other machine types too. But in a permanent magnet machine, it's pretty easy to get an air gap field, a magnetizing field from your permanent magnets that looks like a square wave. You just need radially magnetized magnets. But in a normal machine, we like to pretend anyway that we create an air gap field from our coils that is sinusoidal, and it's the interaction of that sinusoidal and this square field that creates your torque. And what you find is that the sinusoidal field from your winding only interacts with the fundamental harmonic of this square wave field to create torque. So the idea is that if you could create a field from your winding that is also a square wave and control its harmonics so that this square wave travels in sync with the magnet square wave, you can get more torque out of your machine. And so if you do this, you find that you can get about a 33% torque density increase, which is pretty cool trick. So that's one avenue of why you'd want multiple air gap harmonics. The other is bearingless motors, and if you've been hanging around us much, we really like bearingless motors. So the principle of a bearingless motor is that if you add additional harmonics to your air gap field, you can make a force on your rotor. And if you can make a force, well, that means that you can make your motor behave like a magnetic bearing. So a bearingless motor is a motor that also has the functionality of a magnetic bearing, but it doesn't require any extra hardware. So magnetic bearing is a dedicated actuator. In this case, we're using the air gap of our motor as our actuator. And so it turns out that in order to do that, you add a second field to your air gap that is plus or minus 1 pole pairs of your magnetizing field. So we've kind of drawn this over here. This is a 4-pole rotor. So you can see in orange, we've got a 4-pole field. In blue, we've added a 2-pole field, and that's drawn in the blue lines here. And clearly the blue field is adding to the magnets on the right side. It's subtracting from the left side. And so you're creating a net force in the right direction. And again, shamelessly plugging my students, we've got demonstrations set up during the poster session that you'll have to come and check out. The third reason for this is to get wireless power transfer to your rotor. So synchronous machines with wound field rotors need to get current to those coils. And historically, we've used brushes for this. There's also brushless exciters. Well, a third avenue here to getting this power to the rotor is to create a second field in your air gap that is a different number of pole pairs as your torque producing field, and then to install a secondary winding on your rotor that links that field, has a rectifier, rectifies the power, and provides it to the field coil. And this is something that WEMPEC has some history on through Professor Lippo. He has numerous papers, and I just threw a patent up here that he has on this concept. Okay, so those were 3 reasons for why you might want to do this. Now let's talk about what it means to actually do it. How do you do it? What's going on? What's happening? How does it work? And so we'll start by talking about a non-magical motor. Non-magical motor is just, a motor that you learned about in 711 or 713 in our classes. And we'll do this through a study of winding functions. You heard a little bit about winding functions earlier from Professor Johns. Winding function is you can think of it as a physical property of your winding. You've installed coils and slots. They're going to make a field in the air gap when they carry a current. The winding function describes the harmonic content of that field. So here's a winding function right here. If you take your winding function, you multiply it by current, you get MMF acting on the air gap. You multiply MMF times mu naught divided by your air gap length, and you get field. And so we're not going to worry about the complexities of this expression. We're going to just focus on plotting our winding function times our current over and over again, because that tells us all about the shape of this field. It doesn't tell us the magnitude, but it tells us the shape of it. And so you can see here for a fictitiously simple case where our winding only has a single harmonic, H, which would be the number of pole pairs in the machine. This is what the air gap field looks like for phase U. We can't make this field rotate because this is just a single phase field. All we can do is change our current magnitude, so we can make it get bigger, smaller, but it's stuck in place. We'll make it rotate later by adding multiple phases. Now, a magical motor, a motor with multiple harmonics, you take this winding function, you add more terms to it, right? And in this case here, I'm plotting it out where we've got H1 equals 1 again, just like above. And then we're adding an H2 field, and we sum them up to get our total field in the air gap, and it looks a little bit different. It looks a little bit more square, right? Okay, so that's what a single phase is doing. We could develop all the theory that follows in kind of a general mathematical way with variables, but it's not very fun to present or talk about. Instead, we're going to zoom in on 2 example machines for all of this, so we can make cool plots and just think about it conceptually in this way. All the concepts that we talk about here apply to many different phase and harmonic combinations. So the first machine we'll be talking about is a non-magical motor. So it's just a 3-phase motor with 2 poles, normal 3-phase 2-pole motor. Great. The second machine that we'll be talking about in parallel is a magical motor, because it has 6 phases and it makes 2 harmonics. It makes a 2-pole harmonic and then a 4-pole harmonic. All right, so let's talk about that non-magical motor, non-magical 2-pole 3-phase motor. So we've got 3 phases. We rotate that winding function for each of the adjacent phases by 2 pi by 3 every time. And then we excite each of the phases with a current, also spaced out by 2 pi by 3. So this is just the normal motor thing. If we do all this at the same time, phase U has got this winding function, we multiply it by the phase U current, we get the phase U field like we talked about here. We do the same thing for phase V and phase W, and we find that we can make a rotating field in our air gap. So here's our 3-phase winding functions. Here's our 3-phase currents as a function of this angle phi. And then as I'm increasing phi, as phi is changing here, right, we can see that our field will move. And so this is great normal motor theory. And we have 2, we can completely control where this field is located and its magnitude through 2 control handles, the angle phi of our currents and the magnitude of the current I hat. All right, so that's a normal motor. That's review. A magical motor. So now we've got our 6-phase motor, and we've got our 6 phases spread out by 2 pi by 6 radians instead of 2 pi by 3, because we've got 6 phases. Our currents are spread out by the same thing. What happens? Well, here's our winding functions. They look a little bit weird. We've got these kind of weird dancing edges in the bottom from the second harmonic. Here's our 6-phase currents. Great. And then look at the field that comes out. The field has 2 poles. It looks like the field from before. It looks like the field that we saw from our non-magical motor. Well, that's kind of interesting because the winding function clearly also has a 4-pole harmonic. So, what happened? Well, it turns out that if you take these currents and instead of exciting it by 2 pi by 6, you multiply it by 2. So you excite it by 2 pi by 3, which is right here. So this is the same, everything's the same, but now my currents have this 2 in front of them in the phase spacing. Now, suddenly we get a 4-pole field. So this is kind of where some curiosity and some magic comes up, right? This is interesting because we were able to create a 2-pole field with our currents having phase spacing like this and completely control it, get change phi, we can change I hat and completely control where this field is located and its magnitude. And now we can do the same thing also with a 4-pole field. And so you start to get the idea that you could make your phase currents be a superposition of these two slides and independently control your 2-pole field and your 4-pole field. And that's what we're showing here. So now our phase currents have this expression. This is just a general form of what we put on the previous slide. And they've got a harmonic term up here that has a magnitude and an angle. And they've got a term over here that has a magnitude and an angle. Each are creating a different field net air gap. And when you add it together, you get this kind of magical snake-like looking total air gap field, which can do, the kind of things that we were talking about in the previous slides. Okay, so that's pretty neat. And that just sets up the talk that you're going to see in a little bit from Nishant and Anvar on how you design windings that can make that happen. Now, what we're going to talk about briefly is how you connect the drive electronics to the phases to make those currents a reality. And so this was that current expression that we had. And you can see that the most obvious thing is you can take a 6-phase drive and connect it to 6-phase coils, and you're off and running. That's great. But some interesting kind of curious things come up with this if you look at these currents long enough. The first thing, and this is fairly well known and understood, is that if you just do a little bit of effort with rewriting your current expressions, you can group them as 2 3-phase sets. So if you see the shaded green regions, they represent, so if I look just at this column, we've got a 2 pi by 3 spacing here, a 2 pi by 3 spacing here. So these look like a 3-phase current pairing. Same over here in this column, right? 2 pi by 3, 2 pi by 3. And then you can write the same thing for the non-shaded rows. And so you can recognize that, okay, great. I could connect this then as 2 3-phase drives. Drives is called a double star configuration. This is kind of nice. I can get rid of one current sensor because my phase currents have to sum to 0 in each case. I can use standard 3-phase electronics. All right, very cool. Well, it gets a little bit more interesting if you do a little more work on these currents. You can also group them in the manner I've shown up here. So again, this is the same current expressions, just kind of rearrange the rows. And you can see that this looks like 3-phase currents with subphases. So it's like phase U in this green shaded region has subphase 1 and 4. And the subphases have on the right side a common mode current term, and on the left side a differential mode current term. The I1 here is positive, the I1 here is negative, right? And this invites us to create, common mode and differential mode currents are kind of like a classic electrical engineering concept, and thinking about how you connect up amplifiers and all this stuff. So it invites us to create a circuit structure like this on the right, where we can inject a current at this point here. And if this current source is controlled the right way, this current can split evenly between these two windings. And then this current source can inject a current and cause a current to flow in the same direction through both coils. So this allows us to use a circuit-based approach to make these same currents. And the cool thing about this is that it allows one of your inverters to be completely decoupled from the other set of harmonic currents. So it's like this inverter 2 up here. Look at its current expressions. It's just a normal 3-phase drive, right? You can operate your 6-phase machine using an off-the-shelf 3-phase variable frequency drive that already has field-oriented control implemented. So that gets kind of cool when you start to think about this for higher power systems where maybe one of the harmonics you want to create in your air gap needs to carry a lot of power and you want a really reliable standard drive. And the other harmonic maybe needs to carry just a small amount of power, and you can have your custom homebrew circuitry involved. If you've been hanging around our group much, you've seen this structure before. We call this a parallel DP&V circuit for bearingless motors, but I haven't seen it talked about for general multi-phase machines before. So there's another parallel circuit in the interest of time. We'll skip this one. Another interesting concept is you can construct your phases in this Wheatstone bridge arrangement, and then suddenly both inverters have completely decoupled current expressions. And so both are standard 3-phase currents, which is also very interesting. Now, the downside of this configuration is that these current sources in the middle of your Wheatstone bridge end up needing to be isolated single-phase inverters. So anyway, so that's some thought on a single machine. I have just a couple slides here very quickly. What happens if you have 2 machines? So in a bearingless motor, you've got a shaft that you need to support radial forces in 2 planes. It's fairly common that you might want to have 2 machines to control torque and force at both locations. And so obviously you can just, two magical windings, two set magical winding drives, that's great. But it turns out that you can do some, you can play with these circuit-based properties and actually operate the machine with fewer inverters. And this is what my student Jojo is working on, and has a great poster on down in the basement of B330. And so she's come up with 1,393 different ways of connecting 3 inverters to 2 machines, three-phase inverters to 2 machines, and have it actuate the air gap fields in both machines. And she's got a levitation demonstration set up downstairs. Okay, so in summary, multi-phase windings are magical. That's what I'm hoping to convince you of. And you can use it for lots of interesting beneficial things: torque, levitation, wireless power transfer. What I think is very fun and curious here is thinking through how you can control each of these air gap harmonics individually. And the opportunity is that symmetries in these currents present themselves to look at this as a conventional 3-phase motor, even though you're actuating multiple harmonic air gap fields, even though you're actuating as a 6-phase motor. So anyway, come see our posters and lab demos. I'm available to chat virtually. I'm just here hanging out. I would love nothing more than to get an email from you during annual review asking me to talk on Teams or Zoom or something. So you can hit me up. Our WEMPEC staff have also set up a spot for me with a webcam during the poster session. You can come on over to my cam studio and we'll have a little Zoom chat. Yeah, I've got nothing better to do, just hanging out. So anyway, thanks for listening to my talk, and yeah, I'll open it up for questions.
Thanks. Could you go back to slide 17 real quick?
Yes, thanks.
Sorry. So the question comes down to that you want a square wave magnetic field from the windings.
Yeah,
And couldn't you just do that by doing concentrated windings instead of, yeah, there. Couldn't you just do concentrated windings instead of the multi-phase thing to get that? Or
right, yeah, so that's a great question. And there's lots of good subtlety here. So yes, in fact, you can design a 3-phase winding. You can design a single-phase winding that will make a square wave in your air gap. The trick is to make that square wave rotate at the same speed as your magnets intact. And so it turns out that in order to do that, if you just say that you take a 3-phase motor, like a fractional slot concentrated wound motor, and you excite it with 3-phase balanced currents, your harmonics that you create in that square wave, they will all rotate at different speeds. And so your square wave, well, it will look like this waveform, if I can get it will look like this waveform at some angles in the air gap. At other angles, it will be completely decomposed and garbled. And so it turns out that you only are making net torque with your fundamental component, and all the other harmonics of that square wave are just making torque ripple. So the only way to use all of them to make productive torque on your rotor is to have enough phases that you can control each of the harmonics to spin at the speed you want it to spin at.
Hey, this is Hal from Tesla. I just have one question to clarify. Like, what's the winding factor for each pole?
Well, the winding factor?
Correct.
Yeah. Okay, good question. So the winding factor, we can view that as being essentially being the magnitude of the winding factor. It's highly related to the winding factor. You could view it. You can view that as a design decision. So my students Nishant and Amber are about to talk about a winding design methodology to make machines where you kind of specify which harmonics you want to have in your air gap and what their winding factor can be to a certain extent. And so you can design that. That can be part of your decision as a designer, is what winding factor do you want each of your harmonics to have.
Hello, Professor. So I have a question related to the current control while these harmonics are being introduced voluntarily in the field gap. Uh, so would these harmonics be visible to the current control, as in is current of the, say, one of the two inverters which are being connected in a specific configuration, they would have some imprint of that on as a part of their fundamental or their fundamental frequency, right? Because we are introducing harmonics to the field.
Yeah, I think I know what you're asking. So this is a, I could have given like a 2-hour talk just on the current control for this. This is a good question, and it depends on which of those drives you decided to implement this with. So if you go with, this is the current that you want to have in each of the phases of your machine. And if you connect this up just as like a 6-phase machine, right? So this configuration here, or this configuration over here. It turns out that you can use the generalized Clark transform to do, we think about the Clark transform for 3-phase motors, right? It takes 3 phases in, outcomes are D and Q or alpha beta, whatever reference frame you're in. And then they become DC currents if they're at the synchronous reference frame. And so you control a ID and an IQ so that's like a 3-phase system. So for a multi-phase system, you can generalize the Clark transformation to apply to any number of phases. And what you find is that as you increase your phases, you get additional space vectors that you can transform your 3 phases into. So for a 6-phase machine, you get your normal D and Q terms, but then you also get another X and Y term, and the X and Y terms correspond to another harmonic in here. So like if you were to transform this set of currents for 6 phases, this term right here would be picked up in your normal D and Q generalized Clark transform pairing. This term over here would be picked up by the X and Y pairing, and they'd be completely independent of each other. So you can put your current regulators in reference frames that are created by the generalized Clark transform and independently control the harmonics that way. Mm-hmm. Now, when you go to some of these more circuit-based configurations, there's some other kind of magic stuff that transformations that you use, but the end result is that you again get you use feed forward decoupling basically, and you again get a simple control expression that's independent of the other currents.
Okay. Okay, one additional question. So the benefits of this experimentation, one is a torque and increasing torque density. Second is potentially creating a bearingless motor, and third is wireless power transfer. Could you elaborate a little bit more on that? So what specifically is the benefit of
for the wireless power transfer?
Yes.
Yeah. So let me pull that slide up. So this is viewed as a way of enabling wound field synchronous machines. And so if you're set on, hey, I'm going to make a wound field synchronous machine, you got 2 options right now to get that current onto the rotor. One is that you're going to install brushes, and we all know that brushes cause headaches, right? The limited lifetime, there's potentially sparking, all these issues. The second option is brushless exciters. Brushless exciters, this is like a second machine that you've added onto the axial end of your shaft that has its own coils. It's got magnets on the stator, and so it extends axial length. Usually in like in a power generation application, this might be okay. In a vehicle or some kind of mobile or space constrained application, this is terrible. It's also not great if you're trying to push the limits of speed power capability because of aerodynamic issues. So both of the conventional solutions here have problems for getting power to the rotor. This approach here is a way to get power to your rotor without having to add these components. Now, I mean, this certainly has its own challenges as well. you're talking about placing a rotating, you're talking about placing semiconductors on your rotor that are going to rectify it, right? So that's a challenge. You do have to give up some flux carrying capacity in your magnetic circuit to support this field, but I think that's usually pretty minimal. So, and then the next challenge is that you have to add a winding into your rotor that will link that field. Now, this particular example that's shown here on this slide for these pole harmonics, I don't know if the authors mentioned this, but these pole harmonics are going to make it function like a bearingless motor, so it's going to create radial forces. You can of course design your rotor so that that doesn't happen, but it's a compelling alternative to some of these other approaches that have some major drawbacks.
I see. Okay. Thank you for that explanation.
We should probably move on to the next